Welcome to the I Can't Sleep podcast, where I read random articles from across the web to bore you to sleep with my soothing voice. I'm your host, Benjamin Boster. Today's episode is from a Wikipedia article titled Deep Sea. The deep sea is broadly defined as the ocean depth where light begins to fade. At an approximate depth of 200 meters, or the point of transition from continental shelves to continental slopes. Conditions within the deep sea are a combination of low temperatures, darkness, and high pressure. The deep sea is considered the least explored Earth biome, as the extreme conditions make the environment difficult to access and explore. Organisms living within the deep sea have a variety of adaptations to survive in these conditions. Organisms can survive in the deep sea through a number of feeding methods, including scavenging, predation, and filtration, with a number of organisms surviving by feeding on marine snow. Marine snow is organic material that has fallen from upper waters into the deep sea. In 1960, the bathyscaphe Trias descended to the bottom of the Mariana Trench near Guam at 10,911 meters, the deepest known spot in any ocean. If Mount Everest were submerged there, its peak would be more than 2 kilometers beneath the surface. After the Trieste was retired, the Japanese remote-operated vehicle, ROVE, Raiko, was the only vessel capable of reaching this depth until it was lost at sea in 2003. In May and June 2009, the hybrid ROVE, Nereus, returned to the Challenger Deep for a series of 3 dives to depths exceeding 10,900 meters. Natural light does not penetrate the deep ocean, with the exception of the upper parts of the mesopelagic. Since photosynthesis is not possible, plants and phytoplankton cannot live in this zone, and as these are the primary producers of almost all of Earth's ecosystems, life in this area of the ocean must depend on energy sources from elsewhere. Except for the areas close to the hydrothermal vents, this energy comes from organic material drifting down from the photic zone. The sinking organic material is composed of algal particulates, detritus, and other forms of biological waste, which is collectively referred to as marine snow. Because pressure in the ocean increases by about 1 atmosphere for every 10 meters of depth, the amount of pressure experienced by many marine organisms is extreme. Until recent years, the scientific community lacked detailed information about the effects of pressure on most deep-sea organisms because the specimens encountered arrived at the surface dead or dying and weren't observable at the pressure at which they lived. With the advent of traps that incorporate a special pressure-maintaining chamber, undamaged larger metazoan animals have been retrieved from the deep sea in good condition. Salinity is remarkably constant throughout the deep sea at about 35 parts per thousand. There are some minor differences in salinity, but none that are ecologically significant, except in largely landlocked seas like the Mediterranean and Red Seas. The two areas of greatest temperature gradient in the oceans are the transition zone between the surface waters and the deep waters, the thermocline, and the transition between the deep sea floor and the hot water flows at the hydrothermal vents. Thermoclines vary in thickness from a few hundred meters to nearly 1,000 meters. Below the thermocline, the water mass of the deep ocean is cold and far more homogeneous. Thermoclines are strongest in the tropics, where the temperature of the epipelagic zone is usually above 20 degrees Celsius. From the base of the epipelagic, the temperature drops over several hundred meters to 5 or 6 degrees Celsius at 1,000 meters. It continues to decrease to the bottom, but the rate is much slower. The cold water stems from sinking heavy surface water in the polar regions. At any given depth, the temperature is practically unvarying over long periods of time, without seasonal changes and with very little interannual variability. No other habitat on Earth has such a constant temperature. In hydrothermal vents, the temperature of the water as it emerges from the black smoker chimneys may be as high as 400 degrees Celsius. It is kept from boiling by the high hydrostatic pressure, while within a few meters it may be back down to 2 to 4 degrees Celsius. Regions below the epipelagic are divided into further zones, beginning with the bathyal zone, also considered the continental slope, which spans from 200 to 3,000 meters below sea level and is essentially transitional, containing elements from both the shelf above and the abyss below. Below this zone, the deep sea consists of the abyssal zone, which occurs between the ocean depths of 3,000 and 6,000 meters, and the Hadal zone, 6,000 to 11,000 meters. Food consists of falling organic matter known as marine snow, and carcasses derived from the productive zone above, and is scarce both in terms of spatial and temporal distribution. The midwater fish have special adaptations to cope with these conditions. They are small, usually being under 25 centimeters. They have slow metabolisms and unspecialized diets, preferring to sit and wait for food rather than waste energy searching for it. They have elongated bodies with weak, watery muscles and skeletal structures. Because light is so scarce, fish often have larger than normal tubular eyes with only rod cells. Their upward field of vision allows them to seek out the silhouette of possible prey. Prey fish, however, also have adaptations to cope with predation. These adaptations are mainly concerned with reduction of silhouettes, a form of camouflage. The two main methods by which this is achieved are reduction in the area of their shadow by lateral compression of the body and counter-illumination via bioluminescence. This is achieved by production of light from ventral photophores, which tend to produce such light intensity to render the underside of the fish of similar appearance to the background light. For more sensitive vision in low light, some fish have a retroreflector behind the retina. Flashlight fish have this plus photophores, which combination they use to detect eye shine in other fish. Organisms in the deep sea are almost entirely reliant upon sinking living and dead organic matter, which falls at approximately 100 meters per day. In addition, only about 1 to 3% of the production from the surface reaches the seabed, mostly in the form of marine snow. Larger food falls, and studies have shown that these may happen more often than currently believed. There are many scavengers that feed primarily or entirely upon large food falls, and the distance between them is estimated to only be 8 kilometers. In addition, there are a number of filter feeders that feed upon organic particles using tentacles, such as Fraiella elegans. Marine bacteriophages play an important role in cycling nutrients in deep sea sediment. They are extremely abundant in sediments around the world. There are a number of species that do not primarily rely upon dissolved organic matter for their food. These species and communities are found at hydrothermal vents at seafloor spreading zones. One example is the symbiotic relationship between the tube worm Riftia and chemosynthetic bacteria. It is this chemosynthesis that supports the complex communities that can be found around hydrothermal vents. These complex communities are one of the few ecosystems on the planet that do not rely upon sunlight for their supply of energy. Deep sea fish have different adaptations in their proteins, anatomical structures, and metabolic systems to survive in the deep sea, where the inhabitants have to withstand great amounts of hydrostatic pressure. While other factors like food availability and predator avoidance are important, the deep sea organisms must have the ability to maintain well regulated metabolic system in the face of high pressures. In order to adjust for the extreme environment, these organisms have developed unique characteristics. Proteins are affected greatly by the elevated hydrostatic pressure as they undergo changes in water organization during hydration and dehydration reactions of the binding elements. As they undergo changes in water organization during hydration and dehydration reactions of the binding events. This is due to the fact that most enzyme ligand interactions form through charged or polar non-charge interactions. Because hydrostatic pressure affects both protein folding and assembly and enzymatic activity, the deep sea species must undergo physiological and structural adaptations to preserve protein functionality against pressure. Actin is a protein that is essential for different cellular functions. The A-actin serves as a main component for muscle fiber, and it is highly conserved across numerous different species. Some deep sea fish developed pressure tolerance through the change in mechanism of their A-actin. In some species that live in depths greater than 5,000 meters, they have specific substitutions on the active sites of A-actin, which serves as the main component of muscle fiber. These specific substitutions are predicted to have importance in pressure tolerance. Substitution in the active sites of actin result in significant changes in the salt bridge patterns of the protein, which allows for better stabilization in ATP binding and subunit arrangement, confirmed by the free energy analysis and molecular dynamics simulation. It was found that deep sea fish have more salt bridges in their actins compared to fish inhabiting the upper zones of the sea. Deep sea organisms possess molecular adaptations to survive and thrive in the deep oceans. Mariana Hadal snailfish developed modification in the osteocalcin gene, where premature termination of the gene was found. Osteocalcin gene regulates bone development and tissue mineralization, and the frame shift mutation seems to have resulted in the open skull and cartilage based bone formation. Due to high hydrostatic pressure in the deep sea, closed skulls that organisms live on the surface develop cannot withstand the enforcing stress. Similarly, common bone development seen in surface vertebrates cannot maintain their structural integrity under constant high pressure. It has been suggested that more is known about the moon than the deepest parts of the ocean. This is a common misconception based on a 1953 statement by George E. R. Deacon, published in the Journal of Navigation, and largely refers to the scarce amount of seafloor bathymetry available at the time. The similar idea that more people have stood on the moon than have been to the deepest part of the ocean is likewise problematic and dangerous. Still, the deep sea remains one of the least explored regions on planet Earth. Pressures, even in the mesopelagic, become too great for traditional exploration methods, demanding alternative approaches for deep sea research. Baited camera stations, small manned submersibles, and roves, remotely operated vehicles, are three methods utilized to explore the ocean's depths. Because of the difficulty and cost of exploring this zone, current knowledge is limited. Pressure increases at approximately 1 atmosphere for every 10 meters, meaning that some areas of the deep sea can reach pressures of above 1,000 atmospheres. This not only makes great depths very difficult to reach without mechanical aids, but also provides a significant difficulty when attempting to study any organisms that may live in these areas, as their cell chemistry will be adapted to such vast pressures. A continental margin is the outer edge of continental crust abutting oceanic crust under coastal waters. It is one of the three major zones of the ocean floor, the other two being deep ocean basins and mid-ocean ridges. The continental margin consists of three different features: the continental rise, the continental slope, and the continental shelf. The continental shelf is the relatively shallow water area found in proximity to continents. Continental margins constitute about 28% of the oceanic area. The continental shelf is the portion of the continental margin that transitions from the shore out towards the ocean. Continental shelves are believed to make up 7% of the seafloor. The width of continental shelves worldwide varies in the range of zero point zero 0.03 to 1,500 kilometers. The continental shelf is generally flat and ends at the shelf break, where there is a drastic increase in slope angle. The mean angle of continental shelves worldwide is 0 degrees 7 minutes, and typically steeper closer to the coastline than it is near the shelf break. At the shelf break begins the continental slope, which can be 1 to 5 kilometers above the deep ocean floor. The continental slope often exhibits features called submarine canyons. Submarine canyons often cut into the continental shelves deeply with near vertical sides and continue to cut the morphology to the abyssal plain. These canyons are often V shaped and can sometimes enlarge onto the continental shelf. At the base of the continental slope, there is a sudden decrease in slope angle, and the seafloor begins to level out towards the abyssal plain. This portion of the seafloor is called the continental rise and marks the outermost zone of the continental margin. There are two types of continental margins: active and passive margins. Active margins are typically associated with lithospheric plate boundaries. These active margins can be convergent or transform margins and are also places of high tectonic activity, including volcanoes and earthquakes. The west coast of North America and South America are active margins. Active continental margins are typically narrow from coast to shelf break, with steep descents into trenches. Convergent active margins occur where oceanic plates meet continental plates. The denser oceanic crust of one plate subducts below the less dense continental crust of another plate. Convergent active margins are the most common type of active margin. Transform active margins are more rare and occur when an oceanic plate and a continental plate are moving parallel to each other in opposite directions. These transform margins are often characterized by many offshore faults, which causes high degree of relief offshore, marked by islands, shallow banks, and deep basins. This is known as the continental borderland. Passive margins are often located in the interior of lithospheric plates, away from the plate boundaries, and lack major tectonic activity. They often face mid-ocean ridges. From this comes a wide variety of features, such as low relief land extending miles away from the beach, long river systems, and piles of sediment accumulating on the continental shelf. The east coast of the United States is an example of a passive margin. These margins are much wider and less steep than active margins. As continental crust weathers and erodes, it degrades into mainly sands and clays. Many of these particles end up in streams and rivers that then dump into the ocean. Of all the sediment in the stream load, 80% is then trapped and dispersed on continental margins. While modern river sediment is often still preserved closer to shore, continental shelves show high levels of glacial and relic sediments, deposited when sea level was lower. Often found on passive margins are several kilometers of sediment consisting of terrigenous and carbonate deposits. These sediment reservoirs are often useful in the study of paleoceanography and the original formation of ocean basins. These deposits are often not well preserved on active margin shelves due to tectonic activity. The continental shelf is the most economically valuable part of the ocean. It often is the most productive portion of the continental margin, as well as the most studied portion, due to its relatively shallow accessible depths. Due to the rise of offshore drilling, mining, and the limitations of fisheries off the continental shelf, The United Nations Convention of the Law of the Sea was established. The edge of the continental margin is one criterion for the boundary of the internationally recognized claims to underwater resources by countries in the definition of the continental shelf by the UNCLOS. Although in the UN definition, the legal continental shelf may extend beyond the geomorphological continental shelf and vice versa. Such resources include fishing grounds, oil and gas accumulations, sand, gravel, and some heavy minerals in the shallower areas of the margin. Metallic mineral resources are thought to also be associated with certain active margins and of great value. The continent-ocean boundary, COB, or continent-ocean transition, COT, or continent-ocean transition zone, COTZ, is a boundary between continental crust and oceanic crust on a passive margin, or the zone of transition between these two crustal types. The identification of continent-ocean boundaries is important in the definition of plate boundaries at the time of breakup, when trying to reconstruct the geometry and position of ancient continents, e.g., in the reconstruction of Pangaea. The following techniques are used either on their own or more commonly in combination. Gravity data inversion. MOHO depths can be derived by the inversion of satellite gravity data, taking into account the lithosphere thermal gravity anomaly. Crustal thickness can then be derived by subtracting this from the observed base of the drift post-breakup sequence, normally from the interpretation of seismic reflection data. Magnetic stripe data. Most areas of oceanic crust show characteristic stripes due to periodic magnetic reversals during formation at a mid-oceanic ridge. The continental crust is, by contrast, typically magnetically quiet. This method is dependent on stripes being present and will not work for oceanic crust created during the Cretaceous quiet zone. On some magma-rich margins, stripes have also been identified within the transition zone. Seismic reflection data. On normal incidents, seismic reflection data recorded to sufficient depths, the MOHO can in some areas be directly imaged, allowing the identification of normal thickness oceanic crust. Wide-angle seismic refraction and reflection data. The combined use of seismic wide-angle reflection and refraction data give a precise location for the COB by determining the P-wave velocities along a profile. The two types of crust have distinct P-wave velocities. As hydrocarbon exploration moves further offshore to look for remaining potential on passive margins, understanding the location of the COB is critical to predicting possible hydrocarbon occurrence. This is both from the likely location of source and reservoir rocks and the need to model the thermal effects of breakup in basin modeling. Thank you for listening to the I Can't Sleep podcast on Deep Sea.